times this one from the one that we still have, giving us 1, 0, minus 4. This is better in the second position. So now in the range from 0 to 0. So that one there got replaced with 12. And finally 12, which is this one here, plus 4 times 10. 4 times this one plus that one gives us a 0 there. So that 12 is being replaced with 13. So at the end, after this process, we see the ones that are still standing are this one here, and this one here, and this one here, which are just the three basis vectors, often called E1, E2, E3, or something like that. And so we've decided that the span of the four vectors that we started with is really the entire integral lattice, consisting of all integral vectors. It's a high span of E1, E2, E3. That describes the join of the lattices. Now we need to talk about. Okay, so this is very interesting and opens up a entirely new kind of aspect to the lattices. Okay, so what we're doing this process. What we're doing is we're starting with four vectors. Okay, and at the end we end up with three vectors. So we started with a spanning set of four, but the basis that we eventually get to the normal form only has three vectors. So we've lost a vector. Where did we lose the vector? We lost the vector exactly at this spot here. So we generated a zero vector. We still canceled a vector because at every stage we're always doing that. We add a new vector and remove a previous one. But when we get a zero vector, it's not contributing to the ultimate end product. So instead that is to reduce the spanning such that we can't find one whenever we get a zero vector. So the difference between the number of vectors that we start with and the number of vectors that eventually occurs in our spanning is exactly our zero vector. Actually 1 minus 3 times 3, and the 6 was 4 minus 2, so we can stick those in, and again then expand out. We get minus 17 times 1 there, 43 times 2, that's minus 14 of them there, and plus 57, that's plus 43 of them, and number 3s, we have 51 3s, and that's all, and the 4s, just minus 57 4s. At this stage, we have a relationship between vectors 1, 2, 3, and 4 that we originally started with. So this zero row that we have here is telling us a relationship between the original vectors. But we have to kind of go back up the tree and sort of make substitutions to recover what that original relationship was. And we find that the relationship is that the zero vector is really the combination minus 17 times this one, plus 43 times this one, plus 51 times this one, minus 57 times this one. That's the relationship between these four vectors that we have found this way by basically going backwards or going back up our computation, starting from a zero vector, or zero row that we've obtained. Now, this thing can also be rewritten if we bring the 1 and 2 things on one side, because that was the L vectors, and the 3 and 4 vectors on the other side. We get 17, 1 minus 43, 2 equals 51, 3 minus 57, 4. This is now a relationship between the original L vectors and the original M vectors. 69 minus 147. And that is a vector which is both in the L lattice and in the M lattice. And in fact, any vector which is in both of them is going to have to be a multiple of that one. So that the L intersect M, or the meet of these two lattices, is actually something non-trivial, not just the zero vector. There's actually this point that's rather far out there, point 51 minus 69 minus 147. That's sitting in the intersection, and then all integral multiples of it are necessarily also in the intersection. So the intersection is one of our one-dimensional things. So we're in this three-dimensional space. We have two of these two-dimensional lattices, one there, and their intersection or their meet is a one-dimensional lattice. And this is a very general story. And it really opens the door to examine a little bit more carefully what happens with these relations. So we can see that there's another side of the story that's implicit in these lattices, which is about the relations that we have among span and sets. Or more generally, what's the relation that we have between a bunch of M sets? This becomes a very general and therefore important question. Interesting, and we'll investigate that more next time. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening. Good day, I'm Norman Wildberger. This is the first of a couple of videos where we're going to introduce some basic and fundamental concepts from linear algebra into this